Yes. So in last class, we have studied up till the periodic properties. We have started with our atomic radius, ionization potential, electron negativity, and electropositivity. So one of the periodic property we have left behind. So in today's session, we are going to we are going to look about that periodic property also. So let us see and start our today's last session, that is session 6. So in last class, we have left behind a periodic property by name electron affinity. So electron affinity is a very important periodic property. Okay. So what is electron affinity? Let us see the definition here. Yes. Electron affinity means it is the amount of energy released when an electron is added to its valence shell in the neutral gaseous state. Okay. So the amount of energy which is released when an electron is added, here we are adding the electron in the electron negativity, that is the tendency of an atom to attract the pair of electrons, and electropositivity to lose the electron. But here we are supplying some energy to add the electron. Okay. So that is electron affinity, or you can also call it as electron gain enthalpy. Electron affinity, it is also known as electron gain enthalpy. EGA, electron gain enthalpy. Okay. So we are referring by two names. Electron affinity or electron gain enthalpy means both are the same only. Okay. So electron affinity means what? The amount of energy released when an electron is added to its valence shell in its neutral gaseous state is known as electron affinity. Once you recollect about ionization energy, what is ionization energy? The minimum amount of energy required to remove the electron. Okay. But here we are adding the electron. This is quite totally opposite to your ionization energy. Okay, ma. So here the amount of energy released, there the amount of energy needed. Okay, here it is released, there it is absorbed. Okay, so understand the difference here, ma. So the amount of energy released when an electron is added to its valence shell in the neutral gaseous state is known as electron affinity. If you are taking a neutral gaseous element X and we are adding an electron, so upon addition of the electron, the amount of energy released is known as electron affinity. Here EA is known as the electron affinity. This is your electron affinity EA. Okay, so same like your ionization energy, electron affinity also has the same units. Okay, it is also measured in EV. What is EV? Already we have discussed in ionization energy. So that is electron volts. Okay, so it is measured in electron volts. EV means electron volts, or K calories means kilocalories. K calories means kilocalories per mole. Okay, or K joules means kilojoules. Kilojoules per mole. Okay, so kilojoules per mole, these are the units of electron affinity. Okay, so here we are studying about the electron affinity, and here we can see a picture. See here, here the electron which you are adding, when you are adding the electron to its neutral gaseous state atom, some amount of energy is released. Okay, so that energy is known as electron affinity. Here we are adding the electron, we are adding the electron. Okay, ma. So when the electron is added, the energy released is known as electron affinity. Okay, ma. Yes. Now let us see what is its variation in a group. In a group from top to bottom, always group means what? A vertical column. Okay, right? From top to bottom, what will be happening to the size? The size is increasing now slowly. Okay, so when the size is increasing, electron affinity will be decreasing. In a group, size of the atoms are increasing, but electron affinity will be decreasing. Why? Because the electron is very, very far away from the nucleus. When you're adding the electron, the nucleus will not have that much attraction to hold this electron. Okay, to hold this electron, the nucleus is not having that much nuclear attraction over the last electron because of its far away distance from the nuclear attraction. Okay, so The reason is due to its increase in atomic size and less nuclear attraction. Okay, ma. So that's why in a group, okay, the electron affinity will be decreasing. Here you can see, here they are shown from bottom to top. Ma. Bottom to top, it will be increasing. From top to bottom, it will be decreasing. Okay, so that is the electron affinity variation in a group. Always in a group, electron affinity will be decreasing, okay, due to increase in atomic size. Whenever you look at atomic size increasing means opposite to that will be electron affinity. Okay, now let us see how it is varying in a period. In a period, what will be happening to the atomic size, ma? In a period, the atomic size will be decreasing like this. Okay, the atomic size is decreasing. When the atomic size is decreasing, let us see from left to right, electron affinity, it will be increasing because atomic size is decreasing. Only remember that point, opposite to your group. So due to its decrease in atomic size and increase of nuclear attraction on the added electron, because here the last atom is very closer towards the nucleus. Okay, so because of the high nuclear attraction, the electron will be easily attracted and the electron affinity, the amount of energy will be released more. Okay, so that's why in a period, the electron affinity, it will be increasing. Okay, because of its smaller size, the electron affinity will be increasing because of decrease of smaller size and increase of nuclear attraction. Okay, so that is the reason why electron affinity is increasing in a period. Okay, so in a period, the highest electron affinity in the total periodic table, the highest electron affinity is shown by the 7th A group elements. What are the 7th A group elements? Already we have discussed. So 7th A group elements are fluorine, chlorine, bromine, iodine, and astatine, 80. Okay, so these are the 7th A group elements which we have discussed. Okay, ma. So in a group, what is happening to the electron affinity? It is decreasing. So it is decreasing. So that means the highest electron affinity should be shown by which element? Fluorine. Okay, but there is a small reason. The highest electron affinity is shown. It is due to their low atomic size and decrease of the atomic size across the period. Okay, so in the highest electron affinity, it is shown by the 7th group elements, because in a period, when you are coming from lithium also, lithium, beryllium, boron, carbon, nitrogen, oxygen, then afterwards fluorine. Okay, so what is happening to the atomic size? Slowly the atomic size is decreasing. The atomic size is decreasing. When the atomic size is decreasing, fluorine is having very smaller size because of its smaller low atomic size in a period. In a period here we are discussing. That's why low atomic size means decrease of atomic size will be having more electron affinity. Okay, ma. Yes. Now, the highest electron affinity is shown by which group elements? 7th A group elements. Remember this point. Among the 7th A group elements also, the highest electron affinity in the total periodic table is chlorine. Just now I told you. From fluorine, chlorine, bromine, iodine, and astatine, the iodine. Okay. So, here it is iodine, ma. Okay, fluorine, chlorine, bromine, iodine. So here electron affinity is decreasing down the group. Okay, so the highest electron affinity should be shown by fluorine, but due to a small reason, chlorine is showing the highest electron affinity. Highest electron affinity is shown by chlorine. Why? What is the reason? Now let us study here. So here in this answer, it is a very important answer for your 2 marks VSQ question. It is asked for 2 marks VSQ question for your IP point of view. Very important board exam 2 marks question. So why electron affinity of fluorine is less than chlorine, or why electron affinity of chlorine is more? Chlorine is more than fluorine. Both are meaning same. Okay, because chlorine is more and fluorine is less. So anyway, they may ask you, electron affinity of fluorine is less than chlorine. Why? Or explain why electron affinity of chlorine is more than fluorine. Both meanings are same only, na? because we are telling electron affinity of fluorine is more and electron affinity of fluorine is less. So why it is less? Let us understand here. See here, it is due to the low atomic size and strong inter-electronic repulsions. Sorry, my here, print mistake. It is inter-electronic repulsions in 2p shell of the fluorine atom. Okay. And when an electron is added to the fluorine atom, due to inter-electronic repulsions, the energy is liberated. Hence, energy liberated is less than that of the chlorine. That's why halogens having high electron affinity due to their smaller size, only one electron to get the nearest noble gas. Suppose if you take a fluorine atom here, okay, so fluorine atomic number is what? 9. So 9 means 1 is 2, 2 is 2, and 2p5. Okay, ma. In 2p5, in the second shell of fluorine, if you take second shell of fluorine, how many electrons are there? 5 electrons are there. Okay, so totally 5 electrons they'll be filled up here in fluorine. So because of its smaller size, these 5 electrons they are having repulsions in between them, inter-electronic repulsions. In a bench, suppose if you consider a bench can accommodate only 3 students. If you are making 5 students to sit, means it is highly impossible for them to sit comfortably. In the same way, fluorine also, because of its smaller size, there are inter-electronic repulsions between each other. That's why it is having less electron affinity than chlorine. If you consider chlorine, okay, ma. So chlorine is having here, if you take fluorine is having smaller size. See here, only 2 shells are there. But if you consider chlorine will have first shell, second shell, and third shell also. Okay. So first, second, and third. Here the chlorine size is larger. Size is more size. And fluorine size is less size. Okay. So because of its less size, there are inter-electronic repulsions here. Okay. Inter-electronic repulsions are seen in fluorine because of its less size. But if you take chlorine is having larger size. See here, third shell, and here it is only second shell. Fluorine is having only 2 shells. Okay. So because here the size is more of chlorine, that's why chlorine has more electron affinity than fluorine. Okay, that is the reason why electron affinity of fluorine is less than chlorine. This is an important 2 marks VSAQ question, ma. Okay, ma. Understood all of you? Yes. Now let us move on with another important answer, that is ionization potential. Okay, so see here. Here you can see in the fluorine you are having first shell only 2 electrons. Okay, first shell only 2 electrons are there, and in the second shell totally 7 electrons are there. Okay, because 2 is 2, 2p5. Okay, and if you take chlorine, so third shell it is having 3 is 2, 3p5. Here also 7 electrons are there. But here the third shell size is more. But if you take here, size is less. Here inter-electron repulsions are more. But if you take here, inter-electron repulsions are very, very less because of its larger size. That's why chlorine is having more electron affinity than fluorine. Okay, ma. Yes. Now let us see about ionization energy. This is an important LAQ question, ma. Very, very important LAQ question. LAQ question means how many marks? 8 marks. Compulsorily 8 marks. Important question. Without this question, every year there is no examination paper only. Okay. So first, very, very important LAQ question is, what is ionization energy? Okay. So let us study what is ionization energy. Already in the periodic table, periodic properties, we have studied about this. There we have studied only the definition and its variation. But here we have to study in detail about its first ionization energy, second ionization energy, and what are the factors affecting ionization energy. So let us see that. So ionization energy, the minimum energy required to remove the outermost electron from its neutral gaseous atom, is called as ionization energy or ionization potential. For the element, if you are adding an electron, okay, if you are removing the electron, means some amount of ionization energy you are adding then the electron is lost by giving rise to a unipositive ion. Okay, so already we have discussed this one. Okay, the minimum amount of energy required to remove the outermost electron. Remember this word, neutral gaseous atom. In the neutral state only, here there is no charge. Zero, charge is zero. That means neutral gaseous state. Okay, for this neutral gaseous atom only, we are applying the ionization energy to remove an electron. Okay, so then it will give you unipositive ion. Okay, ma. So that is ionization energy. Now, what are the units of ionization energy? Units of ionization energy are EV or kilocalories per mole or kilojoules per mole. Okay, so EV means what? Just now in the electron affinity also we have seen the same units. So these are electron volts. Okay, so EV means electron volts. Okay, electron volts are kilocalories per mole and kilojoules per mole. All the three units we are following same like your electron affinity. Yes, so that is the definition of ionization energy. So in the question they are asking you about first ionization energy and second ionization energy. So let us see what is first ionization energy. So IE1, the minimum energy required to remove one electron, only one electron, remember this point, to remove only one electron from its neutral gaseous atom. This point also you remember, because for ionization energy, we are removing the electron from neutral gaseous atom, is called as first ionization energy or ionization potential I1. Okay, so let us look at that equation. So if you are considering an element M and applying first ionization energy, the electron is lost by giving rise to a unipositive ion. See here, only one unipositive ion. So here it is a neutral gaseous atom because it is not having any charge, zero. The charge is zero. So that's why it is the neutral gaseous atom. Okay. So the minimum energy required to remove one electron from the neutral gaseous atom is called as first ionization energy or ionization potential I1. So M plus I1, same like your general definition only, ma. M plus I1 gives rise to M plus 1 electron. Just we are writing here I1. Why we are removing only one electron here? Okay, so that is first ionization energy. Now, in the question they ask you second ionization energy also. So let us see the definition. Second ionization energy definition. See here, in the picture you can see the electron is released when you are applying the ionization energy. So the amount of energy released when you are removing the electron is known as ionization energy. Okay, ma. Yes, let us see the definition for second ionization energy also. Okay, what is the second ionization energy definition? The minimum energy required to remove the electron, remove second electron. In the previous case, we were removing only one electron. Here, it should be neutral gaseous state, but here for ionization 2, it is unipositive ion. It is called as second ionization energy or ionization potential I2. So there is a lot of difference between I1 and I2. I1 is the minimum energy required to remove one electron, but I2 is remove second electron. There it was neutral gaseous atom, but here IE2, it is unipositive ion, remaining all same. Okay, ma. So let us see with an equation here. The unipositive ion which we got from the first ionization energy we are taking and we are applying again second ionization energy. So as a result, it is losing one more electron. So already it is having one electron loss, means one positive charge, unipositive ion. Again, because of loss of this one electron also, it is gaining one more positive charge. That's why one plus positive charge, and because of this electron, another positive charge. That's why two positive charges. Remember this point for second ionization energy. Same only here instead of only M, we should write M plus. And here instead of M plus, we should write M2 plus, remaining a electron. And here instead of I1, I2. That is the difference mark. So clearly it should be their definition. Then only you'll get the definition 1 mark. Now, in the question, they also asked you about why IE2 is greater than IE1. Okay. So what is that reason? We'll see here, explanation. More energy is required to remove an electron from the unipositive ion. due to decrease of size and increase of nuclear attraction on the outermost electrons in unipositive ion. Okay, ma. See here, hence ionization energy 2 is greater than ionization energy 1. See here, ma, in the picture you can see here, if you are losing this electron means that is I1, right? Now I1, this is I1. So on losing this electron, the ionization energy is I1. Now after losing this electron, I want to remove this electron also. Then I should apply I2. Here, the nuclear attraction is less. See here, this electron nuclear attraction is very less because it is far away from the nucleus. But if you take here, the nuclear attraction is more, na? It is very, very closer towards nucleus. It is more. So because if it's more nuclear attraction, we require more ionization energy. See here, because of due to decrease in the size. Here, as this electron has lost, the size is decreased from second shell. From the third shell, it is decreased. Third shell, it is larger, but second shell, it is smaller. As the size is decreasing and nuclear attraction is increasing on the unipositive ion, that's why we require I2 greater than I1. That is the reason. Okay. So that means because I1, we are removing the electron from the last third shell. That is very, very far away from the nucleus. Easily we can remove. But if you want to remove the electron from the second shell, it is having very, very closer towards the nucleus, less distance, and the nuclear attraction is more, increase of nuclear attraction. That's why IE2 is more than the IE1. This is the reason. So very, very important explanation. For this also, you'll get 2 marks. And that's why the order of IEC is always the I4 greater than I3, then I2, then I. That means when you are moving inside and inside, it is coming closer towards the nucleus. Due to increase of nuclear attraction, we require more and more ionization energy than the first ionization energy. Okay, ma'am. So now let us see what are the factors affecting the ionization potential. So ionization potential depends upon the following factors. What is it? Atomic size, nuclear charge, screening effect, and extent of penetration of subshells, and stable electronic configuration. These are the 5 factors which are affecting the ionization potential. So let us see in detail what are the 5 factors. Yes, yeah. First factor is atomic size. So when the atomic size increases, the distance between the nucleus and the outermost electrons increases and the nuclear attraction decreases. Okay, so on the outermost electron, nuclear attraction is decreasing. So less energy is required to remove the outermost electron from the atom. Okay, hence atomic size increases, the ionization potential decreases. So we can understand clearly from this picture here. See here, because as the atomic size is increasing, what is happening? The distance from the nucleus is increasing because the nuclear attraction is decreasing means what is happening? We require only less energy. But here nuclear attraction is high. We require more energy. So that's why here as the atomic size increases, ionization potential decreases. We require only less energy to remove the electron. So that's why atomic size is inversely proportional. Here this symbol is called as proportionality symbol. Proportionality symbol. Proportional. So that is proportional. And 1 by, if you are writing that constant variable value means that is inversely proportional. So atomic size is inversely proportional to 1 by IE. So this point also you have to clearly mention. So if you write this box total relationship, then only you'll get 1 mark for this explanation. You should show this box also. As the atomic size increases, ionization energy decreases. They are opposite. Okay. If atomic size decreases, ionization energy will be increasing. So remember that point. Okay. Yes. Next factor is nuclear charge. And when the nuclear charge increases, we require more energy. Why? Because the outermost electrons are held strongly. They are strongly attracted by the nucleus. That's why we require high energy. That's why ionization potential will be more. So that's why nuclear charge is directly proportional to the ionization energy. Okay, ma. So nuclear charge is directly proportional to ionization energy. So here they are directly proportional. Both are in the numerator place. If nuclear charge increases, ionization energy also increases. If nuclear charge decreases, ionization energy also decreases. Okay, ma. So that is the second factor which is affecting ionization energy. Now let us see about the third factor. What is screening effect? The decrease of nuclear attraction on the outermost electrons is called as screening effect. When the number of electrons in the inner orbit increases, the screening effect increases and the nuclear attraction on the outermost electrons decreases. So less energy is required to remove that electron. Okay, so that means here if you take an atom, okay, consider this is the first shell, second shell and third shell we are considering. In third shell only one electron is there, consider that. And in second shell, what is happening? Consider as 4 electrons are present in second shell. Okay, ma. I'm considering 4 electrons. I want to remove this electron means these 4 electrons, what they are doing, they are screening this last electron. That means they are protecting this last electron. Screening means nothing but protecting. Okay, protection. So they are protecting the last electron from which? From the nuclear attraction. So here easily I can remove this electron. Ionization energy becomes very, very less. That means if screening is more means ionization energy is less. So that's why here the nuclear attraction over the outermost electrons decreases. So only less energy is required. That's why less ionization energy is required if screening effect is increasing. See here. Hence, screening effect increases means ionization energy decreases because the innermost electrons are more. The outermost electrons nuclear attraction is less. Easily we can remove. So less ionization energy we require. Okay, ma. So that is the reason of increasing of screening effect and decreasing of ionization energy. So we should also write the relationship. Screening efficiency of the orbitals is in the order of S, P, D, and F. Okay. So here, why only S orbital is having more screening effect? Why? Because here S orbital is having spherical shape and P is having dumbbell shape. If you look at this picture, you can clearly understand, ma. See here. Yes, S orbital is having spherical shape and P orbital is having dumbbell shape. D orbital is having double dumbbell shape and F orbital is having here no peculiar shape. Okay, ma. So it is not peculiar, not familiar. See here. See here the electrons in the S are spherical. Okay. Because they are spherical means every electron will be present around the nucleus. But here electrons, only 1 or 2 electrons may be present in the P. So that means S is having more screening effect than P, than D, than F. Because they are having dumbbell shapes. They are not uniformly distributed like an orbit like S subshell. Okay. And if you take, so that's why S is greater than, having greater screening effect than P, than D, than F. This also you should mention, very, very important. Okay. And last, next factor is extent of penetration of subshells. Okay. So penetration of subshells is, here the extent of penetration of subshells is also of the same order. S greater than P greater than D greater than F. Here also same, because of its spherical shape, it is having more penetration power. Because of their dumbbell shapes, they are having less penetration power. If the penetration power is high, the electron will be very, very closer towards the nucleus. Here, S is having spherical shape. That's why the electron is very, very closer towards the nucleus. Here, that's why they are strongly attracted. So high energy is required to remove the electron. That's why high ionization energy follows the penetration power as S greater than P greater than D greater than F. So the same order like your screening effect. So that is the screening effect. The next is last factor which is influencing the ionization energy is stable electronic configuration. So the elements with completely filled and half-filled configurations are more stable. This is very, very important. Completely filled and half-filled configurations are more stable. Okay, so if more stable is there means we require high energy, high ionization energy is required to remove the electron from the atom. So that's why high ionization energy is required. So let us understand with this example here. Here N means here what is it? Nitrogen. N means nitrogen. So in nitrogen, the atomic number is what? 7, right? 7. So 1s2, 2s2, 2p3. So let us see this last 2p3 electrons. So what are the last 2p3 electrons? CM. This is the last 2p3 electrons subshells because p will be having 3 orbitals now. 2p3. Okay. So here in each subshell, 3 electrons are there now. So one shell we should write with single electron. Each cell you should write single electron. We should not pair up. Okay, ma. See here we are writing with single electron. Okay, first shell single electron, then second shell another electron, then third shell another third electron. So here if it is having 3 electrons means it is having which configuration? Half filled na? Half filled. So totally P can fill up 6 electrons. P can fill up 6 electrons if you pair up here. Okay, if you pair up 6 electrons it can fill up, but here we are filling half filled. Only 3 electrons it is filled up, that's why half filled. And if you consider here neon atomic number is what, ma? 10. Okay, neon atomic number is 10, that's why neon 1s2, 2s2, 2p6. Totally 10 electrons. 2 plus 2, 4. 4 plus 6, 10. Okay. So now let us see what is the number of electrons in 2p. So let us see here. In p, we are having 3 orbitals, right? And we are having 6 electrons now. So first, each orbital you should fill up with single electron. Okay. We are filling up with a single electron each. Then fourth electron will be paired up with first electron. Fifth electron will be paired up with second electron. Sixth electron will be paired up with third electron. Now they are completely filled up. Okay, in nitrogen they are having completely filled configuration. In nitrogen half filled, in neon completely filled. According to us, half filled and completely filled, they are more stable. More stable means we require high ionization energy. So that's why this stable electronic configuration will be depending upon more ionization energy. Okay, ma, this is the last factor. This is also very, very important. Write this example also in the exam. Very, very important. Now, how ionization energy is varying in a group and period. This is also you should mention. See here, in a group, ionization energy decreases from top to bottom. So what is happening in a group? The atomic size is increasing now. If atomic size is increasing means the distance between the nucleus and the center of the nucleus and the last shell is increasing. Okay. So because distance is increasing means nuclear attraction is less. Easily we can remove this electron from the last shell. So that's why ionization energy is less. The energy required is less because atomic size is increasing. Ionization energy decreases in a group. Okay. So in a group it is decreasing due to its increase of atomic size and decrease of nuclear attraction. Increase of atomic size. Yes, atomic size increasing. And nuclear attraction is, what is happening? It is decreasing. Decrease of nuclear attraction on the outermost electrons. Now, how does it vary in a group? In a period. In a period, it is increasing due to decrease of atomic size and increase of nuclear attraction. Just oppositely. In a period, what is happening to the atomic size? It is decreasing. Slowly, it is decreasing. So the atomic size is decreasing. Because atomic size is decreasing, the nuclear attraction is increasing. Decrease of atomic size, the nuclear attraction increases. That's why ionization energy increases. Okay, ma. So that is the reason how ionization energy is varying in a period and group. Okay, ma. Yes, here ionization energy is increasing in a period and decreases down the group. Ma. Understood? Yes. Now let us see about metallic nature and non-metallic nature. Metallic and non-metallic nature. What is metallic nature here? The highly electropositive or low electronegative elements. Okay, they are called as metals. High electropositive, that is known as metals. Always 1A and 2A group elements are only metals. See here, we can see all the red color part. Red color part is nothing but metals. Red color elements are metals. Only 1A, 2A group elements are the strongest metals here. Strong metals. The high electronegative are low electropositive. High electronegative means they are non-metals. Are non-metals. Mostly 6th and 7th group. Here we can see 6th and 7th group elements are strong non-metals. Okay, ma. So variation of pentalic nature and non-metallic nature in a group and period. Let us see in a group, metallic nature increases because as we move down the group, the highest, strongest metal is cesium. So it is increasing. In a group, metallic nature increases. If metallic nature increases means non-metallic nature decreases. Remember that point. It is due to increase of atomic size, electropositive nature, and variation in a period. In a period, metallic nature decreases and non-metallic nature increases. Totally opposite to your group. Metallic nature decreases and non-metallic nature, it increases from left to right. It is due to increase of electronegativity. For metallic nature, increase of electropositivity, but here increase of electronegativity and decrease of electropositive nature. Okay, ma. So total opposite to your group, you should write, ma. So in metals, mercury, and in non-metals, bromine, they exist as liquids at room temperature. Okay, ma. See here, we can see in this picture, here is your bromine. Okay, so this is your bromine. Bromine is existing as liquid at room temperature, and mercury is the metal, but still it is existing as liquid at room temperature. Where we will be using mercury? In your thermometers, right? In thermometers, we are using this mercury. So it is existing as liquid at room temperature. Yes, now let us see about the nature of oxides. So here, this is also an important 2 marks VSCQ question mark. So the binary compounds of oxygen with other elements are called as oxides. The binary compounds of oxygen with other elements are called as oxides. We are having 3 types of oxides here, ma. Basic oxides, acidic oxides, and amphoteric oxides. Basic oxides, acidic oxides, and amphoteric oxides. Let us see that. First one is basic oxide. Basic oxides are generally found by metals. Metals means always basic oxides. They dissolve in water to form alkaline solutions. Okay, so how? Let us see here. So if you take Na2O and we are reacting with H2O, we'll get 2NaOH. So here NaOH is a base now. Already we know. In your 10th class, you may have studied NaOH, KOH, and CaOH taken twice. So if you are taking Na2, sodium hydroxide, and reacting with water, you will get a NaOH, sodium hydroxide base. Then if you take calcium oxide and react with water, we'll get the calcium hydroxide. It is also a base. Base means it should have compulsorily OH. OH is there means that is a base. So basic oxides are always metals because sodium, magnesium, and calcium, these are metals. Okay, ma. Yes. Now let us see about the acidic oxides. So let us see about the acidic oxides also here. Acidic oxides are carbon dioxide, nitrogen, P2O3, P2O5, SO2, SO3, Cl2O. These are acidic oxides. Always the 6th group and the 7th group elements, they'll form acidic oxides. Here, carbon is 4th group, nitrogen 5th group, 6th group, 5th, 6th group elements, all the non-metals, they'll form acidic oxides. Remember that point, ma. All the first group elements, 1A group elements and 2A group elements, they'll form the basic oxides. Amphoteric oxides are here. This ZNO, Al2O, PbO, and SNO. These are the amphoteric oxides. And neutral oxides are CO, NO, NO2O. Remember this oxides, ma. Now let us see with our diagonal relationship. Very, very important diagonal relationship. Okay, so what is diagonal relationship? The first 3 members of the second period What are the second period elements? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So in that first three elements, these are the first three elements, they will show much similarity with the second element of the next group. It is known as diagonal relationship. So this phenomenon is observed only in 1A, 2A and 3A groups only. So let us see those examples here. Yes, lithium will show similarity with magnesium. This is the third period and this is the second period. This is second period and magnesium is third period, second element. Here also second period and third period. Second period and third period elements, they are showing diagonal relationship. So let us see here. CMR, second period element, lithium, it is showing diagonal relationship magnesium of third period. Okay. Beryllium is showing diagonal relationship with the aluminum. Boron is showing diagonal relationship with silicon. Okay. So diagonal relationship elements will have similar physical and chemical properties. What are the reasons to show the diagonal relationship? Due to the similar size of atoms or ions. That is the first reason. And due to similar electronegativities of the respective elements. Okay, and similar polarizing power. What is polarizing power formula? Polarizing power means the ratio of ionic charge by ionic radius square is known as polarizing power. Because of these three reasons, they are showing the diagonal relationship. This is an important VSAQ question, 2 marks VSAQ question. Sometimes they may ask you for, or they may ask you for 4 marks SAQ question also. Very, very important. Okay, so SAQ question. Okay. Now let us see about the next important answer from this chapter is lanthanide contraction. Very, very important answer, that is lanthanide contraction. What is lanthanide contraction? Let us understand here. So here, lanthanides means 4F series elements already we have seen. At the bottom of the periodic table, they will be present, right? So at the bottom of the periodic table, we are having this lanthanides, okay, the 4F series elements, okay. So the slow, steady decrease of size of atoms or ions among lanthanides is known as lanthanide contraction. See here, the size is slowly decreasing because it is decreasing. Okay, so the slow steady decrease is known as lanthanide contraction. It is due to differentiating electron enters into 4f shell, which is having dispersed shape and is having poor screening effect. It is not able to screen properly. That's why the size is decreasing. So what are the consequences? Very, very important answer, ma. Very, very important answer for your IP point of view. For your 4 marks, they'll give you SAQ question. What is lanthanide contraction? The slow, steady decrease of size in the size of atoms or ions among lanthanides is known as lanthanide contraction. It is due to differentiating electron enters into the 4F subshells of penultimate shell, which are in dispersed shape and having poor screening effect. So what are the consequences? Let us see. Due to lanthanide contraction, the crystal structure and other properties of the elements, they are coming very, very closer to each other. As a result, it is difficult to separate them from the mixture. That means their size will be becoming same. So if you take this element, zinc and hafnium, these are having similar size. The size is same. Okay, because the size is same here, that's why that is unable to separate these elements from each other. We can't separate zinc from hafnium or hafnium from zinc because of lanthanide contraction. Okay, now let us see what is the next consequence of lanthanide contraction. So the elements of second and third transition series resemble each other more closely than the elements of first and second transition series. So what are those elements? See here. Zirconium and hafnium, they are showing same size. Molybdenum and wolfram, they are also showing same size. Niobium and tantalum. Zr means zirconium. Zirconium. Already I have given in your periodic table, long form of periodic table, all these elements. And HF means hafnium. 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 And MO means molybdenum. Molybdenum. Okay, molybdenum. And W means what? Wolfram. Wolfram. NB means niobium. Niobium. Ta means tantalum. These are the elements, tantalum. Okay, so all these you can remember, ma. So zirconium, hafnium, they are having same size. Molybdenum, wolfram, they are having same size. Niobium and tantalum, they are having same size due to lanthanide contraction. Okay, they are also having the same properties. As the size of lanthanide decreases from cerium to lutetium, the covalent character of MOH bond increases, hence the basic strength is decreasing. So that's why cerium hydroxide is most basic while lutetium hydroxide is less basic. Here we can see lutetium hydroxide. Lutetium hydroxide is very, very less basic. It is least basic than cerium hydroxide. So these are the consequences of lanthanide contraction, ma. Very, very important. So with this, we have completed our chapter, ma. This periodic classification. So from this chapter, the expected important LAQs, SAQ questions. Let us see here. The first, already in the previous class, I gave you some of the SAQs and LAQ question till syllabus where we are covered. And in today's class, till where we are covered, till the last end of this chapter, the important LAQ question is define first ionization energy, IE1, and second ionization energy, IE2. Why second ionization energy is greater than IE1. Discuss all the factors affecting ionization energy. Already I gave you, ma. Okay. Then next is explain different types of oxide, giving one example each. Okay, this is also very, very important. 2 marks VSAQ question. Write the properties of transition elements. This is also important for 4 marks question, ma. In the Friday's class, I have explained this one. What is lanthanide contraction? What are its consequences? It is also an important 4 marks SAQ question. The next important answer is explain diagonal relationship. What are its reasons? This is also important VSAQ question. Electron affinity of chlorine is more than that of fluorine. This also they may ask you for 2 marks VSAQ question, ma. And what are rare earths and transuranic elements? In the Friday's class, we have discussed. This is also an important VSAQ question. So practice all these answers for your second chapter, ma. So whatever I gave you in the Friday's class and today's last Monday class of this periodic classification, the total weightage of this periodic classification is 8 plus 2. 8 plus 2 is the weightage of this chapter. That means you may get a LAQ question and you will get one SAQ question, VSAQ question. So this is the weightage of periodic classification. Total 10 marks you'll be getting from this chapter. Okay, ma. You're getting 10 marks from this chapter. Okay. So thank you, ma. So please end the class.